Good afternoon, everyone. Thank you for joining Mr. Ish for this next video, a continuation from the video on imaginary numbers. Today our main focus will be talking about complex numbers. Very quickly, complex numbers are in the form represented by the letter Z. Complex numbers have both real and they have imaginary parts. So they are found in this form x plus yi, or it's the same thing as saying x plus iy. Whether you say iy or yi, it's the same. But the x over here represents the real part, the real number part. Okay? And this portion over here represents the imaginary number portion. And you know z over here represents a complex number. So complex numbers are made up of two parts, a real part and an imaginary number. And the fact that they have these two parts is why they are called complex, because they're a composite of two different types. Our focus today is to focus here on the complex numbers and some of the operations involved with them and some of the trigonometric aspects of these. But before we do, I want to quickly review some of the material I presented yesterday with regards to imaginary numbers. And you know imaginary numbers are represented by the letter I. So let's look briefly over here. Yesterday I mentioned as imaginary number having the properties that if you were to take an even square root of a negative number, you'd end up with having an imaginary number. You see the 16 would come out as a 4 and the minus would come out as an I. So you'd get an answer 4i. But one of the main properties of imaginary numbers are that if you take the square of a positive square of an imaginary number, you'll get an answer -1. But technically, if you think about that in terms of real numbers, that's impossible. If you take any real number, if it's a negative and you do a square of that, you'll end up with a positive answer. Likewise, if you do a square of a positive number, you'll get still a positive answer. So with real numbers, there's absolutely no way that you can do a positive square exponent and still end up with a minus answer. You cannot do that with real numbers, but with imaginary numbers, this property shows that if you do a square of an imaginary number, you end up with a minus answer. So this right here is fundamental to the imaginary number concept. And as a quick example, in extension to the examples I presented yesterday, I want to just present a few more before we actually get into the concept of complex numbers. If someone were to ask you to solve a question which looked like this, let's say I to the power of -1, how would you go about doing that? You would have to basically convert this into a reciprocal. And just like how you would rationalize radicals, you can rationalize a complex number. You would take the same number, you'd multiply it in the denominator and you'd multiply it in the numerator, and you'd carry that through. You'd get I divided by I square. And you know, in that previous video I mentioned I to the 1 is equal to I, and I square is equal to -1, I cube is equal to minus I, and I to the 4 is equal to 1. Things that you were supposed to memorize. Now if you look at the same question we're looking over here, right, we're carrying it through by means of rationalizing. We've brought this into this form over here, and you know you can actually simplify this. You get I on the top and I square is a -1, so you end up getting a minus I. So I to the power of -1 gives you a minus I. But what happens if I were to make the question just a tad bit harder? How would we proceed with that? I'm going to show you that. What if the question you were asked is this? You have to solve I to the power of -11. How would you go about doing that? Well, there are multiple ways. Let me show you one way. You can write this as 1 over I to the 11, because the minus exponent is a reciprocal. And now you can rationalize it. Rationalizing an imaginary number is same as rationalizing a radical. You take the same thing, you multiply it, numerator and denominator. Carry this forward. You'll get I to the 11 on the top divided by I to the 22. Now it's not a difficult matter. You've gotten rid of the minus exponent. Now you just break these down individually. I to the 11 is the same thing as saying I square to the power of 5 times I. And I to the 22 is the same thing as saying I to the power of 2 to the power of 11. Right, 2 times 11 is a 22, 2 times 5 is a 10, plus this 1 gives you that 11. Now you just have to carry this out. I square is a -1, -1 to an odd exponent times I, right? -1 to an odd exponent, which is 5, odd exponent. I square is a -1 to an odd exponent, 11. Now it's just a matter of finishing this up. A minus to an odd exponent stays minus, and on the top you get an I. Remember, minus to an even exponent becomes positive, but minus to an odd exponent retains a negative character. Here on the bottom we have -1 to the power of 11. we get a minus 1. So what's our final answer? It's an I. Alright, so minus numbers to odd retain minus. Minus numbers to an even exponent become positive. Let me show how we could have solved this in a different way. The same question. How about this? I to the minus 11 is the same thing as saying this. I square times minus 6 times I. Look over here. 2 times minus 6 is a minus 12. Minus 12 plus this hidden 1 is a minus 11. Easy, right? No rationalizing involved over here. Now look over here. I squared is a minus 1 to the power of minus 6 times I. Minus 1 to the power of minus 6 is just the same thing as saying 1 over a minus 1 to the power of 6. Remember, this minus 6 exponent means only 1 over. A reciprocal. 1 over a minus to an even exponent will lose that minus, and your final answer will be positive I. You see, we've gotten a positive I over here. So keep all of this in mind, how these type of questions play out. Also look over here. A new thing which I mentioned here with regards to the previous video was the concept of rationalizing, which I showed you in the example right before this. Let me show you some more rationalizing with imaginary numbers before we actually begin to talk about complex numbers. If someone told you to rationalize this 2 plus I, it's easy. You always have to use the properties of conjugates or the concept of conjugates. The conjugate is always the opposite sign of what you have. You would rationalize this by multiplying the top and the bottom by the opposite sign. If it's 2 plus I, you're multiplying the top and the bottom by 2 minus I. And then you just carry this onward. 2 minus I on the top, and on the bottom you'd multiply all of this. 2 times 2 is a 4, minus 2I plus 2I. Remember, when you always use conjugates, these intermediate terms go away, which is a big plus. So what's your final answer? 2 minus I over 4 minus I squared, and I squared is a minus 1, so this becomes a plus 1. So you get 2 minus I over 5. Easy, right? Remember, the whole concept of using conjugates is you're always rationalizing with the expression but having an opposite sign. Not hard. I want to show one more example of this form, and then let's get right into the business of complex numbers. Keep in mind that complex numbers can undergo any of these operations, like a plus bi. You can add them up or minus them up as you would any other numbers. How about this? 1 minus I minus 2 plus I. You just open it up and add it out as you would. 1 minus 2 is a minus 1. And this minus I would become a minus 2I. See? Not too hard. But with regards to rationalizing, look at this question. 3 minus I over 3 plus I. You want to rationalize it. Take the item on the denominator and switch the signs. And then carry it all forward. What do you get? Let's look at the top. You'll get 9 minus 6I. You see, you don't have conjugates here, so you're not going to eliminate the intermediate term. Plus I square over, on the bottom you have conjugates, you will have no intermediate term. And here on the bottom you'll have 9 minus I square. Finish this up. You'll get 9 minus 6I minus 1. Remember, I square is equal to minus 1, so you'll get 8 minus 6I. And here you'll get 9 plus 1 minus I square is a minus times minus 1 becomes plus 1 over 10. You can simplify all of this in terms of being a multiple of 2. Everything is even number. You'll get 4 minus 3I over 5. So keep these operations in mind. Keep the concept of conjugates. Keep the concept of rationalizing in your mind. You're rationalizing this just as you're rationalizing radicals. Let's move forward now to the concept of complex numbers. Complex numbers are given this symbol z. Not too hard to remember, but you want to think of them in this form. Z is equal to x plus yi. I don't like to write I first, though in textbooks you'll see x plus iy, but this is how I like to write it. Here's the real part, here's the imaginary part. But what do we do with all of this? X plus yi, you have the real part here, which is considered the x-axis part. Alright, the x-axis here represents your y-axis item. So how do you plot this out? You're going to look at exactly like how you plot out regular numbers. You're going to go x units this way, and then you're going to go y units this way, depending on the signs. You're going to make your little dot over here, which represents the intersection of these two coordinates. Make a line towards the origin. Here's your angle, and this right here, R, is going to represent your modulus. Alright, R is going to represent your modulus. And I'm going to talk very quickly soon about what a modulus is. A modulus is basically just the distance from that point to the origin. Not hard at all, but this is called the modulus. But why is this practical in terms of trigonometry and the whole concept of complex numbers? Because this is a means for diagrammatically representing complex numbers. And I'm going to show you an example right now of how this plays out. The example is this. You are being asked to plot 4 plus 3i and determine the modulus. Alright? And this is how you're going to do it. Exactly as if you're looking at, here's your x component, here's your y component. You're going 4 units to the x on the right because everything is positive, and you're going 3 units to the top. The intersection of these represents a line to the origin, which is your R. This right here is your x, here's your y. Look, here's my x over here, here's my y component. Alright? How do you determine R? R is basically determined exactly in the same formula as the distance formula. You're going to do the x squared plus y squared, and you're going to do the square root. You're going to do 4 squared plus 3 squared, and you're going to root it. You'll get 16 plus 9, you'll get root 25, and you'll get 5. So here R is equal to 5. The modulus of this complex number is equal to 5. And then there's something over here you have to be paying attention to, is the angle. What's the angle? The angle is called the argument. Alright, the argument of this complex number is represented as the angle, as an argument or a debate. So these are two terms you should be aware of. Argument over here and modulus, as I mentioned before. How do you determine the angle? The angle is always equal to the inverse tan of your y divided by your x. Alright, y divided by x. Tan theta is equal to your argument. Theta is equal to inverse tan of y over x. What's y over here? 3. What's x value over here? 4. So the inverse tan of 3 divided by 4. What do you get? You need your calculator. 0.75 inverse tan, you get 36.9 degrees. So the argument over here is 36.9 degrees. All of this will play out as we show more of the features of complex numbers. But I want to show you some more examples, because complex numbers plotting, this is, this right here, the whole concept of showing this is called a complex plane. This whole Cartesian coordinate system is called a complex plane. You're showing in a Cartesian manner how you can graphically represent complex numbers. I want to run through several of these examples before I show you an additional application of all of this. Here is an example of a complex number. Z is equal to 2 minus 5i. And the question is, you have to determine the R value, the modulus, and you have to determine the argument. All of these you have to determine. The first step you should always do is think about graphing these, plot them out. The first number, the real part, always represents your x component. The imaginary part represents your y component. Okay? You're looking 2 units. It's a positive 2, so you're looking 2 units here. But it's a minus imaginary component, so you're looking 5 units down. And you make an intersection over here. Remember, we're talking about a complex plane over here. In the complex plane, the x-axis, right? The x-axis represents your real axis, okay? Your real axis. Your y-axis is representative of your imaginary axis. So here I'm plotting the real numbers along the x-axis, and I'm plotting the imaginary numbers along the y-axis. And here I've plotted 2 comma minus 5i. You connected it here. You connected, which represents your r. Alright, your r is your modulus. Make a little line. Of course, I'm not drawing things to scale over here. This makes a right triangle, and here's your argument. You basically have to determine the r and the theta. The r is easy. You basically take your 2 numbers, square them, and take their square root. 4 plus 25. What do you get? A root 29, right? So this is equal to your r, which is also can be represented as this. Z within these 2 lines. Z. Okay, your modulus. How about determining the theta? Theta is equal to arctan or inverse tan of y over x. What's my y component over here? It's a minus 5. See, it's a minus 5. Minus 5 over 2. Take the inverse tan of this. Minus 5 divided by 2. 5 minus divided by 2. Inverse tan it. I get a minus 68.1. I get a minus 68.19 degrees. But I know just by graphing it, I'm looking in quadrant number 4. I need to get a better answer than this. I take minus 68.19 and add it to 360 degrees. I get 291 291.8. So this thing is the same as saying 291.8 degrees. So my argument is 291.8 degrees. My modulus was a root 29, right? 2 square plus 5 square root 29. Not too hard. Let's look at more examples. What if someone said that this right here is your complex number, z equals 4i, and you have to determine the r value, which is your modulus, and you have to determine the argument, and you have to plot it. How do you go about doing that? Well, you can recognize this by converting into the x plus yi format, alright? Where's my x component over here? There is no x component. So you can rewrite this as saying 0 x plus 4i. Here's my yi component, here's my x. So there is no x component here, but you can look at this as 0 comma 4. See, you can look at it as 0 comma 4 as a clue. It tells you you're looking right here on your y-axis in this direction, and that's your plot here of this point 4i. But what's your z value going to be over here? It's not too hard. I'm sorry, your r value, your modulus. Modulus is going to be 0 square plus 4 square and root of that. It's going to be just 4. But what about your theta? Theta is always equal to y over x, which over here happens to be what? 4 over 0 undefined. So that it's undefined. It's telling you your angle must be pi over 2 or 90 degrees, because you're exactly on this y-axis, 0, 90, 180, 270, 360. So you know exactly 90 degrees. Do 90 and you take a tan of it, you get undefined. So you know 90 was your angle. So your argument here is 90 degrees. Your modulus here is 4 degrees. How about this next question? The question is this. Your complex number is minus 9. You know you can rewrite this as minus 9 plus 0i, because your imaginary part is non-existent, it's 0i. Remember, it's x plus yi. Well, you know you got your x value here, but you got no y. You can look at this as minus 9 comma 0. That clues you in exactly where your point is. It's right here on this axis, on the negative x-axis. You got to determine the r. It's going to be the real component square plus the imaginary component square, and you can do the square root of that. Square root of 81 is 9. So you know your value r, your modulus is 9. Not too hard. But what about your theta? Theta is going to be your inverse tan, or the arctan, y over x. What's your y component over here? 0. 0 over 9, which is inverse tan of 0. It's going to be either 0 degrees or it's going to be what, 180 degrees. Just by knowing exactly where you are, you have to say my angle here is pi, 180 degrees, because you're not in this first quadrant where you would assume the 0 degree answer. You're going to assume the 180 degree answer. So your theta value, your argument is pi. See, minus 9 comma 0, you're in right between quadrants number 2 and 3. So the most logical answer is pi, not 0. I'll present another example before we turn things up slightly one notch higher. The question is this. The complex number is minus 4i. X and yi components, the real and the imaginary. You gotta plot it and you gotta determine the modulus and the argument. Whenever you see something like this, just look at it. Here's my x component, here's my y component. What am I seeing? I'm seeing a minus 4 comma minus 4, right? And that clues you in how to plot it. 4 this way, 4 down this way. Make your dot. Here's your r, here's my y, here's my x, and here's my theta angle. And you know you got a 90 degree. Right? Remember, this is a complex plane, not a real plane, but a complex plane, an imaginary plane involved in along with the real plane. X-axis is your real plane, your y-axis is your imaginary plane. But how do you find r over here? It's always equal to your x component or your real component square, and add it to the imaginary component squared, and you take the square root. So you're doing a minus 4 square plus a minus 4 square, and you're square rooting all of that. What are you going to get? You'll get a 16 plus 16, 32. You'll get a 4 root 2. Your modulus over here, this is your modulus. You can also present it as that. Here's your modulus is equal to 4 root 2. But what about your angle? Your angle is going to be inverse tan of your y divided by x. What's my y? It's a minus 4. Don't say it's a minus 4i. It's a minus 4. Minus 4 divided by minus 4, which is a what? Inverse tan of a 1. See, you're getting an inverse tan of a 1. Minus 4 divided by minus 4 is a 1. Look over here, you do 1 and you inverse tan and you get 45 degrees. You're basically getting a 45 degrees. But now you gotta be smart and say, where is this for? What type of 45 degrees? Am I looking at a 45 here, 45 here, 45 here, or second quadrant 45? Or the third quadrant 45? What's a third quadrant 45 degree angle? It is 225, which is 5 pi over 4. So your angle here is going to be 5 pi over 4. That's your third quadrant 45 degree angle, which is your argument for this. These questions are not too hard. They may seem a little complicated, but they're not. Now in this next bit of this video, I'm going to show you another aspect on top of all of this. So this is where we start laying the real foundation for difficult types of questions with regards to complex numbers. We're not going to be talking about those actual difficult parts yet, but we're laying the foundation for the aspect which will be presented in the next video. But this is now the foundation for all of that. Now we're talking about here about polar forms. As you know, I've already presented this, the argument, the modulus. Another way of looking at y and x with regards to your complex number, which always has the form x plus yi or iy, it don't matter how you say it. You know, you can say x is always equal to or cosine theta. Think about it. Cosine theta is equal to adjacent or hypotenuse. Shuffle that around, you'll get x is equal to r cosine theta. Just the basic definition for a cosine function. Now what about y? Y will equal to r sine theta, right? Again, sine theta is equal to y or r, therefore y is equal to r sine theta. I haven't introduced anything new over here that you don't already know of. I'm just now laying the groundwork for something I'm about to present. And you know here, with regards to the argument, theta is always equal to the inverse tan of y over x. So given all of this, let's start developing a polar form for complex numbers. It's not going to be anything hard, and you know r is your modulus and this right here is your argument. If z is equal to x plus yi, right? If z is equal to x plus yi and I've shown you x is equal to this and y is equal to this, right? And you have both of these, then substitute. What is z also equal to? Z is equal to r cosine theta, which represents your x part, plus r sine theta, which represents your y part, and you got to not forget this I, right? Look at this. All I've done is substitute this in place of x, this in place of y, and now look what I'm going to do. I'm going to isolate r. See, r is a common term and all, the modulus is common in both of these. R parentheses cosine theta plus I sine theta. All I did was just write the imaginary part first and the sine theta, and this is equal to your complex number. This right here is shown over here, derived with regards to that. This right here is your polar form of complex numbers. The polar form. Polar form means that it's going to have the trigonometric aspects along with the Cartesian aspects demonstrated in this single equation. Now this single equation right here will have the highest applicability when it comes to complex numbers and the material I'll present in your next video. But I want to show you how to determine and develop polar forms using some of the examples that will come next. Look over here. So this right here is your polar form of the complex number z. Now the question is this, you have to write this right here, minus 1 plus I in its polar form. You have a complex number here, z. All you gotta do is write this in the polar form. And to do these type of questions, you're gonna need to determine two things. You need to determine the r and you need to determine the argument. You'll have to determine the modulus and the argument. For each of these questions I'll present, you have to determine these two. After you've determined these two, you can present your answer in the polar form. The first part you should always do is think about plotting it. Look over here, you have a minus 1 plus 1i. Isn't that the same thing as saying minus 1 comma 1, which you know how to plot? Minus 1 here, 1 here. Here's my minus 1 comma 1. Draw it with regards to the origin. Here's your theta, here's your 90 degrees. Here's your 1, here's your minus 1. What must r be? R must be the square of these. 1 plus 1 square minus 1, 1 square, doesn't matter. The square will make it a positive anyways, and you get root 2. So your modulus here is equal to root 2. I've determined the modulus here, root 2. Now the next thing you must determine is theta. Remember, we're right here trying to determine the technique for determining and demonstrating the polar form of complex numbers. Theta, as you know, is always the inverse tan of your y over x. But what's your y value over here? It's 1. What's your x? It's minus 1. So you're doing the inverse tan of minus 1. Do the inverse tan of minus 1. Use your calculator. I know it's going to be a 45 minus 45. Inverse tan, you get minus 45. Minus 45. But you got to be smart over here by determining which type of 45 degree angle. You know you're in second quadrant, so you got to look at your second quadrant 45 degree angle, which must be 3 pi over 4. Material that I presented in the Fundamentals of Trigonometry video, where you should memorize these numbers, these radians. 3 pi over 4 is 135 degrees. So now you got your argument, you got your modulus, you have everything you need to write this in a complex form, in your polar form. Your answer is going to be this. Z is equal to R root 2 cosine 3 pi over 4 plus I sine 3 pi over 4, and you're done. Not too shabby, right? So you start with a question which looks like this. You got to determine the R and the argument. Always use a graph to help align you as with regards to which quadrant you're in. Proceed, and then at the very end write your complex form, your polar form. The question is this. You're given minus 1 over 4 minus root 3 over 4i, and you have to write this complex number in its polar form. And you know you got to determine R, and you have to determine the argument. First step always is to look at this in terms of coordinates. I see a minus 1 over 4, and then I see a minus root 3 over 4. And that clues you in exactly where you are. Remember, we're not drawing to scale. You have a minus, minus, minus x, minus y, so you're in the third quadrant. Let's just imaginarily, right, make this our point. Minus 1 over 4 this way, minus root 3 over 4 this way. Connect it over here. You know, this is here your R, and this right here is your argument. Well, you got to find the R first, and you know R is going to be the square root of these individual components squared. Minus 1 over 4 squared plus minus root 3 over 4 squared. Minus 1 over 4 squared is a 1 over 16. Minus root 3 over 4 is a 3 over 16. What do you get? Root of 4 over 16, which is a root of 1 over 4, which is a 1 over 2. You can see that, root 1 over 2. I've determined the modulus. I want to determine the argument next. Argument is always equal to inverse tan y over x. Let's do this on the calculator. What's my y value here? Look over here at your coordinate form. Root 3 over 4. Let's put it all in decimals. Minus root 3 divided by 4. I get a minus 0.433, whatever number. I'm going to divide this by minus 0.25. I get a 1.73. Inverse tan it. I'm getting 60 degrees. 60. Theta is equal to 60 degrees, or pi over 3. But is this really our right answer? We're looking here in quadrant number 3. Quadrant 1, 2, 3, 4. What's our 60 degree angle in quadrant 3? Pi over 3, 2 pi over 3, 4 pi over 3. Here's my real argument here, 4 pi over 3. Now how do we write all of this in its polar form? This is how we're going to do it. Let's look right over here in this space. Our polar form will be the z is equal to our modulus 1 over 2, parentheses, remember this part right here, cosine 4 pi over 3 plus I sine 4 pi over 3. And we're done. Here's my answer. Done. The polar form of this complex number. The complex form, the polar form. The question is this. Our complex number is a minus 5i. We have to determine this complex number's polar form. We have to convert it. First thing you want to do is convert it into this type of form right here. You see a 0 minus 5i. This clues you in exactly to what your coordinates are. You have a 0, you have a minus 5, which clues you in exactly where you are in terms of this map. Complex plane. You're right here, 5 units down on the y-axis. This right here is 0 comma minus 5i. You got to determine the r over here, which is the square of the individual components x and the y. 0 square plus minus 5 square. Do all of that and you'll get 5 anyways. That's your r. What's your theta? You're on a 90-degree angle right here. 270 degrees. You don't need to bother doing inverse tan and all of that. You know this is 0 degrees, this is 90, this is 180, this is 270, 360, and you can keep going on by 90s. You know theta is 3 pi over 2. You got everything you need now to convert this complex form into the polar form. The polar form is going to be this. Z is equal to r, which is 5. And now your polar coordinates. Cosine 3 pi over 2 plus I sine 3 pi over 2. Just keep in mind the I, the imaginary part, is always sticking with the y part. It always attaches to the y. Because the y-axis is your imaginary axis and your x-axis is your real axis. Okay? Here's your polar form of this complex form. Last example coming up and then we'll be done. So here's our complex number. Our complex number is z is equal to minus 9. Always try to write it out into this form, x plus yi, and that tells you you are dealing with a minus 9 plus 0i. See, here's my real part. I have no imaginary part. Imaginary part is none, so it's 0. This clues you in into your coordinate form, minus 9 comma 0, minus 9 comma 0, which clues you in into the plotting part. Here's your minus 9 comma 0. You can't draw a triangle here because you have no second dimension. You only have one dimension. You don't have the second dimension in terms of graphing. You got to determine r first. The r is always the real component squared plus the imaginary component squared. Minus 9 squared plus 0 squared. Calculate this all out, you'll get a 9. That's your r value. Theta, not too hard. We don't have an intermediate angle over here. We have something right on the axis. Here's 0 degrees, 90 degrees, 180 degrees, 270 degrees. My theta is 180 degrees, which is what? Pi. You could have calculated it out using your inverse tan. Theta is equal to inverse tan y over x. What's my y value over here? 0. 0 over 9. And you do inverse tan of 0. Look, put 0 and you do inverse tan, you'll get 0 degrees. But you know you gotta look at the proper 0 degrees. You're either looking at 0 or you're looking at pi. And you have to pick pi simply because you're in this side of the axis. You're on this side of the quadrants. So you have to automatically go for this as your answer. Not 0 degrees but pi. Last step is to write this all in the polar form. Your polar form will be, you can say z is equal to r, which is 9. And then you do cosine pi plus I sine pi. You can go from the complex form to the polar form, and you can go from the polar form back to the complex form simply by opening this up. Let's open this up. You'll get 9 times cosine of pi. 180 cosine is always minus 1. Plus sine of 180 is 0. 0i. Open this up. You get minus 9 plus 0i, which is the same thing as saying minus 9. So all the examples I've shown you in the polar forms, if you were to open up the polar form, the brackets, multiply everything, you'd always end up back to the complex form. So the complex form and the polar form are interchangeable. This whole process in between just shows you how they are interchangeable. I hope you enjoyed this video. I certainly did. Easy material for now, but it becomes a little bit more complex as you will see in the next video. Please like, subscribe and share, and have a nice day.